Welcome to Microlecture 51 on alkene addition reactions. This one is dihydroxylation with osmium tetroxide. Okay, so here we're talking about the addition of a reagent called osmium tetroxide to alkenes, and this is a two-step process. We won't talk much about the second step. Let's focus on the addition of the osmium tetroxide in a moment when we talk about the curved arrows. Okay, so we'll only be focusing on step one there. And for the stereochemistry, we want to indicate syn or anti across the double bond and whether or not the product is chiral or achiral. So what's going to happen with the carbon-carbon double bond in this case? It's a dihydroxylation. OH groups are going to add across both carbon atoms of the carbon-carbon double bond. Remember, benzenes are unreactive. They don't react like alkenes, so we leave the benzene alone, and we add the OH groups across the double bond in a syn fashion. Now, the mechanistic details on the last slide are going to help you understand why it's syn, but for now, let's just predict a few products and decide whether or not that stereochemistry leads the product to be chiral or achiral. In this case, there's a hydrogen atom pointed back there, so this is a stereocenter, but we also, with equal likelihood, will form the syn addition on the opposite face with the OH groups adding on the dash. So we've got a 50-50 mix of enantiomers, a racemate, and it's achiral. And a few more examples here. We've got, in this case, the possibility for OH groups to add on the same face wedge, and with equal likelihood they could add to the same face dash. Okay, so just to clarify then, that means the ethyl here is back and the ethyl here is forward. The hydrogen here is back and the hydrogen here is forward. We get a 50-50 mix of these. In this case, we've got a nearby R group, and that's going to dictate the stereochemical outcome. The osmium tetroxide can only approach from one face. All right, and so the resulting structure is going to have the hydroxyls adding only to that side, to the dash. And the methyl, therefore, is going to be on the wedge, and the product is chiral. Notice we started with something chiral. And then in the third example here, we can add the two OHs on the dash side, which means the phenyl group over here would be on wedge, but we could also have added those two groups on wedge. Phenyl would be on dash. What we're noticing as well is the stereochemistry of the alkene, such that what we have here with our high and low priorities, high priority over here, high priority over here, is an E alkene. All right, so we want to keep these two groups on the same face of each other. Just make sure that they're on the same face as each other in the final drawing. That way, if you were asked to state the absolute stereochemistry or the absolute R or S stereo configuration of the resulting structures, you would be able to get that correct. All right. In any event, the product is achiral because of the fact that it is a 50-50 mix of possible enantiomers. All right, so as far as the mechanistic details here, it's an interesting reaction. Osmium tetroxide looks like this. there's a lot of d orbital electrons for osmium, and so it can form this compound with 4 oxygens around it and 16 electrons around the osmium atom. And so what's going to happen is the osmium tetroxide is going to approach the double bond, and in this case, only the backside face is accessible because we have this R group blocking one face of the carbon-carbon double bond. And so it's a cyclic mechanism that looks like this, and it results in an intermediate structure that looks something like this. Okay, so it's a concerted cyclic mechanism, and that's causing the syn addition. And because the osmium tetroxide can approach only from one face, if you have a nearby R group blocking the other face of the alkene, we can see some stereochemical consequences. Okay, and so in this case, we get only this as a product. Okay, as a major organic product, and it's chiral. Okay, this last part happens in step 2. You don't need to know any details about this step mechanistically or otherwise.